Polyols from cashew nut shell liquid, CNSL, building blocks for bio-based additives and polymers. The increasing demand for sustainable materials has intensified research into renewable feedstocks for polymer synthesis. Among these, cashew nut shell liquid, CNSL, has emerged as a particularly attractive and industrially relevant bio-based resource. CNSL is obtained as a byproduct of cashew nut processing and represents a low-cost, abundant, and non-edible biomass. Its utilization aligns strongly with circular economy principles by valorizing agricultural waste streams into high-value chemical intermediates. One of the most promising applications of CNSL lies in the synthesis of polyols, which serve as essential building blocks for a wide range of polymeric materials, including polyurethanes, polyesters, coatings, adhesives, and surfactants. The unique chemical structure of CNSL components distinguishes them from other renewable polyol sources. Specifically, the presence of a rigid aromatic ring combined with a long, flexible aliphatic side chain enables the design of materials that simultaneously exhibit mechanical strength and flexibility. This dual structural characteristic is rarely found in conventional bio-based polyols, which typically provide either rigidity or flexibility but not both. As a result, CNSL-derived polyols have gained considerable attention as functional intermediates for advanced material applications. Composition and structural features of CNSL. Cashew nut shell liquid is a dark brown, viscous liquid extracted from the shell of the cashew nut, which originates from the tropical tree Anacardium occidentale. The shell constitutes a significant fraction of the total nut mass, typically ranging from 55% to 65%, and global production of cashew nuts generates millions of tons of this waste material annually. CNSL is primarily composed of phenolic lipids, namely anacardic acid, cardyl, and cardinol, along with minor quantities of methyl cardyl and trace urushiol derivatives. The composition of CNSL depends strongly on the extraction method employed. When extracted under mild conditions, the product, known as natural CNSL, contains a high proportion of anacardic acid. In contrast, high-temperature processing leads to decarboxylation of anacardic acid into cardinol, producing what is referred to as technical CNSL. This transformation significantly alters the reactivity and suitability of the material for subsequent chemical modifications. Structurally, CNSL components possess a phenolic aromatic ring substituted with a C15 alkyl chain that may contain one or more unsaturations. Additionally, functional groups such as hydroxyl groups and, in the case of anacardic acid, a carboxylic acid group contribute to the chemical versatility of these molecules. The aromatic ring imparts rigidity and thermal stability, while the long aliphatic chain provides flexibility and hydrophobicity. This combination enables CNSL derivatives to function as both structural and performance-enhancing components in polymer systems. Chemical transformation pathways to CNSL-based polyols. The conversion of CNSL into polyols involves the introduction or enhancement of hydroxyl functionality through chemical modification of its reactive sites. These transformations primarily target the phenolic hydroxyl group, the unsaturated alkyl chain, and the aromatic ring. Modification of the phenolic hydroxyl group represents one of the most direct approaches to generating polyols. Although the phenolic hydroxyl group can participate in polymerization reactions, its reactivity is lower than that of aliphatic alcohols. Consequently, strategies have been developed to convert this group into more reactive hydroxyl functionalities. Etherification reactions, for instance, enable the introduction of diol structures, although certain reagents used in these processes raise toxicity concerns. More sustainable approaches include hydroxyalkylation via the ring opening of cyclic carbonates such as ethylene carbonate. These reactions are typically catalyzed by amines or basic catalysts at elevated temperatures and proceed with high conversion efficiency. An important advantage of this method is its compatibility with carbon dioxide utilization, as cyclic carbonates can be synthesized from CO2, thereby contributing to carbon recycling. Another widely employed strategy involves the formation of epoxidized derivatives through reactions with epichlorohydrin. The resulting epoxy groups can then be opened via hydrolysis, amination, or thioepoxy reactions to yield polyols with increased hydroxyl functionality. Amination reactions, in particular, produce beta-hydroxylamine structures that exhibit high reactivity and can enhance the performance of the resulting polymers. In addition to modifying the phenolic hydroxyl group, the unsaturated double bonds in the alkyl chain provide an effective route for increasing hydroxyl functionality. Epoxidation of these double bonds using oxidizing agents such as peracids or hydrogen peroxide generates epoxide intermediates, which can subsequently be converted into polyols through ring opening reactions. These transformations can be carried out under acidic or basic conditions or through nucleophilic attack by amines or thiols. While epoxidation is a versatile method, challenges such as incomplete conversion and the handling of peroxide reagents must be carefully managed, particularly in large-scale applications. The aromatic ring of CNSL also serves as a reactive site for functionalization. Reactions such as the Mannich condensation enable the introduction of amino and hydroxyl functionalities, producing polyols with enhanced adhesion and mechanical properties. Other transformations, including electrophilic aromatic substitution and azo-coupling, further expand the range of accessible CNSL-derived polyols. These modifications often result in materials with improved thermal stability and resistance to environmental degradation. In addition to small molecule transformations, CNSL can be incorporated into polymeric intermediates such as phenolic resins. Cardinol formaldehyde resins, for example, can be synthesized under acidic conditions and subsequently used as polyol precursors in polyurethane formulations. These resins combine the inherent rigidity of aromatic structures with the flexibility of aliphatic chains, resulting in materials with balanced mechanical and thermal properties. CNSL-based polyols in polymer applications. CNSL-derived polyols have found extensive applications in polymer science, particularly in the synthesis of polyurethanes and polyesters. Their unique structural features enable the design of materials with tailored properties for specific applications. Polyurethanes represent one of the most significant application areas for CNSL-based polyols. These polymers are formed through the reaction of polyols with isocyanates, resulting in materials characterized by the presence of urethane linkages. The properties of polyurethanes can be finely tuned by adjusting the ratio of soft and hard segments, which are determined by the structure of the polyol and the isocyanate used. CNSL-based polyols contribute to the soft segment due to their flexible alkyl chains, while their aromatic rings enhance the rigidity and thermal stability of the material. In polyurethane foams, CNSL-based polyols have demonstrated improved performance characteristics, including enhanced compressive strength, uniform cell structure, and increased thermal stability. The presence of multiple reactive sites in these polyols facilitates rapid crosslinking, leading to higher crosslink densities and improved mechanical properties. Additionally, the hydrophobic nature of the alkyl chain contributes to moisture resistance, which is beneficial for insulation and structural applications. CNSL-derived polyols are also widely used in polyurethane coatings, where they provide excellent abrasion resistance, chemical stability, and adhesion to substrates. Functional modifications, such as the incorporation of phosphate groups, can further enhance corrosion resistance and surface protection. These properties make CNSL-based coatings particularly suitable for applications in harsh environments. Beyond polyurethanes, CNSL-based polyols are increasingly explored in the synthesis of polyesters. In the context of environmental sustainability, biodegradable aliphatic polyesters have attracted significant interest due to their ability to undergo hydrolytic and microbial degradation. The incorporation of CNSL-derived components into polyester structures introduces aromatic content, which improves mechanical strength, while the flexible alkyl chains enhance chain mobility and potentially facilitate biodegradation. This combination is especially valuable in the development of aliphatic aromatic copolyesters that balance performance and degradability. In addition to their role in polymer synthesis, CNSL-based polyols are used in the formulation of surfactants and specialty additives. Their amphiphilic nature, arising from the combination of hydrophobic alkyl chains and hydrophilic hydroxyl groups, enables their use in non-ionic surfactants and emulsifiers. Furthermore, CNSL derivatives can function as plasticizers, lubricants, and reactive diluents, contributing to improved processing and performance characteristics in various industrial formulations. Advantages and limitations. The use of CNSL-based polyols offers several advantages, including their renewable origin, chemical versatility, and ability to impart desirable properties such as thermal stability, flexibility, and hydrophobicity. These attributes make them highly attractive for the development of sustainable polymer systems. However, certain challenges must be addressed to fully realize their potential. The inherent dark color of CNSL can limit its application in products requiring light or transparent finishes. Additionally, the unsaturated alkyl chains are susceptible to oxidation, which may lead to discoloration and degradation over time. The use of certain hazardous reagents in traditional synthesis routes also raises environmental and safety concerns. To overcome these limitations, ongoing research focuses on the development of greener synthesis methods, stabilization strategies, and purification techniques. Approaches such as hydrogenation of unsaturated chains, incorporation of antioxidants, and discoloration processes are being explored to enhance the performance and applicability of CNSL-derived materials. In conclusion, cashew nut shell liquid represents a highly promising renewable resource for the production of bio-based polyols and advanced polymeric materials. Its unique molecular structure, characterized by a combination of aromatic rigidity and aliphatic flexibility, enables the design of materials with tailored and enhanced properties. Through a variety of chemical transformation pathways, CNSL can be converted into polyols with diverse functionalities, making it a versatile building block for polyurethanes, polyesters, coatings, and surfactants. Despite certain challenges related to color, oxidation, and processing, the continued development of sustainable and efficient modification strategies is expected to further expand the industrial adoption of CNSL-based polyols. As the demand for environmentally friendly materials continues to grow, CNSL stands out as a key contributor to the advancement of sustainable polymer chemistry and the reduction of reliance on fossil-based resources.